Hello everyone, welcome to lecture 5 of week 9 of the course Power Network Analysis, in which we continue with our discussion on the second last module, which is fault analysis. And in this discussion, we will understand a very important aspect of application of Thevenin's theorem for performing fault analysis. So we'll understand the basis of why Thevenin's theorem. We all very well understand what is Thevenin's theorem. We'll understand its application of the theorem on the fault analysis perspective. Till the previous lecture, we were continuing our discussion on fault analysis, and we had very extensively talked about why a synchronous machine, conventional synchronous machine, could be a salient pole machine, non-salient pole machine, why it has a variation in its value of synchronous reactance XS for cylindrical pole machine or XD for a salient pole machine. Why does it have a variation, and how this variation results in distinct behaviors during a fault, specifically in terms of the subtransient period where the fault current tends to be high, followed by a dip in the transient period, and finally, if things are to remain stable, then the current reaches a steady state value. So the current value decreases from subtransient to steady state period in terms of the fault current, if we were to say, whereas the value of X, it tends to be at its minimum in the subtransient period and having a maximum value along the steady state period. And we also briefly talked about the difference or purpose behind doing fault analysis and the last module, which is stability analysis. Fault analysis is all about figuring out the worst case or worst possible fault currents during faults in a power network, whereas and that's the reason why fault analysis is a subtransient period, because only during subtransient period we will be able to know what is the maximum current. In stability analysis, we are all focused on whether the system would remain stable following a fault or a disturbance, the system here being the power network. And stability analysis is essentially a transient period study in which the machine's transient reactances would come into picture. Power flow we have talked about in the previous module extensively, and it basically pertains to a steady state study wherein we don't at all go inside the machine terminal. We retain ourselves only till the bus, which could behave as a PV bus if voltage control of synchronous generator is not lost, or it converts to PQ bus when the excitation control is lost. So having said that, let us see what is Thevenin's theorem and how does it apply. Fault, we have already seen that it is any failure or abrupt or interruption in terms of flow of load current. That event would be called as a fault, and those faults essentially appear in because of intentional or unintentional operations. Intentional operations when power network element like a transformer or a line has to go into a maintenance, scheduled maintenance, or unintentional in the case because of some weather disturbance, aging effect, or unforeseen event, the network element itself might stop working or performing satisfactorily, which might interrupt the flow of current from the source to the load. And in general, these faults can be classified as symmetric or asymmetric faults. Symmetric faults are those faults where all the three phases, let's say if I have a transmission line with phases A, B, and C, all the three phases are equally affected. If one phase current is going down because of this interruption, then similar quantum of interruption would also happen in the remaining phases. So in a way, the system or the power network still tends to remain symmetric or balanced for three-phase fault, and that's the term where symmetric terms comes in. There are other types of asymmetric faults which we haven't talked about yet, but hopefully we will talk about it when in the next lecture. And one important aspect which we discussed in the previous lecture example was that those of you who have not gone through the previous lecture, please go through it first before, and only after that you will be able to understand the aspect that I'll talk about. Is that in the previous lecture and example, we considered a numeric study wherein the actual fault current, which was the post-fault current, it was essentially superimposition of the pre-fault current, which was the normal load current, plus the additional fault current that would come in as the fault occurs. So basically, we inherently made use of the superimposition notion that, and we sort of came up with the final fault current to be the addition or superimposition of the previous fault current before the fault and the fault current as and when the fault occurs. And Thevenin's theorem, on the other hand, also enables this superimposition, and that's where it would be very useful to find the post-fault currents in all the symmetric or asymmetric fault that we will talk about. So I'll start with a very basic discussion that given what is Thevenin's theorem or what is the application of Thevenin's theorem. Thevenin's theorem is a theorem which indicates that given a electrical network with sources of the same frequency, the network can be sort of reduced, or equivalent network can be created for this actual network with several sources and loads operating at same frequency to a simpler source and a load combination, where the source would be called as the Thevenin source and the corresponding impedances that would appear across 2 points of interest from which the Thevenin's theorem or application is to be seen would be called as the Thevenin's impedance. So that is Thevenin's theorem essentially is a way of reducing the complex representation of the actual power network. For fault analysis, Thevenin's theorem application indicates or suggests that the change in voltages or currents that would be observed in the network due to a fault, those change in voltages and currents would be equal to the changes which would have been caused by the equivalent Thevenin's pre-fault condition. And Thevenin circuit, it would consist of a voltage source and a corresponding equivalent impedance, which is a Thevenin's impedance in itself. So essentially, if the summary of this statement is that if a fault occurs in a power network and we are interested in finding the change in voltages, the bus voltages, or change in line currents or the bus currents, then these new changes, which are the fault currents and the corresponding post-fault voltages, these can be obtained through a simpler analysis, in which the simpler analysis would just have one equivalent Thevenin's pre-fault voltage source and one equivalent Thevenin's impedance. We don't have to consider the entire 1000 bus network to find these change in currents or voltages in the event of a fault. That is what the summary of Thevenin's theorem application is. So in a way, Thevenin's theorem purpose is to reduce the pre-fault network into a simpler network which is easier to handle, and that network would consist of an equivalent Thevenin voltage and an equivalent Thevenin impedance. So if that is the understanding, let us see, before we go into fault analysis, let us see whether Thevenin's theorem actually helps in finding these change in voltages or currents apart from fault conditions. So yes, during any other switching also it should apply, because this statement is a generic statement. The term fault here could be replaced by any other disturbance for that matter. So what I have considered here is a very simple circuit which has a 100-volt DC source. All elements here are ideal, and there is a branch A and B connected as shown in the figure, in which there is a switch, and at t less than 0, switch S is open. That means the impedance between A and B, it is infinite. There is no current flowing in between the branch A and B. The actual current which is present in the circuit before the switch S is closed is IB0, which is the source current, and it's very imperative that IB0 by applying KVL would be equal to 100 volt divided by 10 ohm the first series impedance plus the other 10 ohm second series impedance, which is overall equal to 100 by 20 equal to 5 ampere. That means before the switch is closed, that is at t less than 0 when the switch is open, the source current is 5 amperes, and we want to find the change in current. The statement is, or the intent is to find the change in current from the battery or the source, which is this IB0, after the switch is closed. So before the switch is closed, as I have indicated, 5 ampere is the source current, and if I find the potential difference between node A and B, then this potential difference between VA, so basically if I have to find VA minus VB, I can apply KVL between A and B, which would tell me that VA is equal to, as I'm going along the direction of flow of current, so IB0 current is flowing over here, I'll have a voltage drop of 10 IB0, and finally I have reached point B, which is VB. So this would give me VA minus VB, which is VAB, equal to 10 IB naught, which is 10 into 5 equal to 50 volt. So before the switch is closed, the voltage across nodes A and B is 50 volt VAB. And this VAB happens to be also equal to the Thevenin voltage across node A and B before the switch was closed. So we'll come to this aspect little later. Now when the switch is closed, the new current that would flow IB can be found by corresponding equivalent impedance or resistance of this combination circuit, which is denoted by 5 parallel 10. So basically 5 parallel 10 is the corresponding equivalent resistance between nodes A and B, which would give us 5 into 10 by 5 plus 10, which is 50 by 15, also same as 10 by 3 ohms. So 10 by 3 ohms is the equivalent resistance between A and B. When gets added up with 10 ampere, I have 7.5 amperes as the new current after the switch is closed. So essentially the change which has happened compared to switch open, where IB naught was 5 ampere and now IB naught, IB being 7.5 amperes, because the current has increased, because the overall circuit impedance as seen by the corresponding voltage source has gone down. So the current change has happened by 2.5 amperes. Now, is this current change also possible to obtain applying Thevenin's theorems? Let's see that. So by Thevenin's approach, as I mentioned in the previous slide, VTH is the voltage across node A and B, which is 50 volt. So I can sort of find, so given that my Thevenin voltage source is known, to find the Thevenin impedance, voltage sources would be shorted and current sources would be open circuited. Voltage sources being shorted, why voltage sources are shorted while finding Thevenin impedance? The answer is simple. When I'm finding Thevenin's impedance, all my sources should not deliver any quantum of energy or power. So basically when I am shorting my voltage source, the potential across that source itself is zero, so it won't be able to deliver any amount of power or energy, and none of the circuit elements would be consuming any quantum of energy or power from the voltage source. So basically I'm trying to make my voltage source as passive as possible. Current sources, why are they open circuited? When the current sources are open circuited, the corresponding current cannot flow, and hence the power or energy cannot be delivered by the corresponding current source, and that is the reason why we are trying to make them passive. One could also argue why voltage sources are only shorted, why are they opened? If you try to open up a voltage source, potential will still exist, and that's the reason why circuit won't remain passive. Same thing for current source, why current sources are not shorted, because still current can flow and it could pass on through some other circuit element. So that's the reason why we're trying to make it as passive as possible. So to find the Thevenin impedance between A and B, we have only one voltage source as shown over here. So it is actually shorted. And when I short this and try to find the Thevenin impedance between A and B, and this Thevenin impedance is to be found in the pre-fault condition. Please remember about the pre-fault case. So in the pre-fault case, before the fault has occurred, if I have to simulate a similar condition here, then my switch still has to remain open. I don't have to close the switch and find the Thevenin impedance. So in that case, if the switch is open, that means this particular element or circuit is not present, and 10 ohms in parallel give me ZTH or ZAB as 5 ohms. So now I can redraw the circuit between node A and B while retaining the element or part where the disturbance is going to happen through a Thevenin equivalent source, which is VAB equal to 50 volt in series with ZAB, which is equal to 5 ohms. Then I have node A and node B, and the switch here is present, and I have a 5 ohm circuit resistance in between. So this is my new Thevenin pre-fault condition before the switch S was closed. Now when the switch is closed, then after the switch is closed in the Thevenin circuit, after S is closed, the current that would flow through branch IAB or between A and B would be IAB, would be equal to, again by KVL, it would be equal to VAB by ZAB plus 5, which is 50 by 10 equal to 5 amperes. That means IAB current after the switch was closed, before the switch was closed, IAB is 0 because current cannot flow. After the switch is closed, using Thevenin's theorem, the new current that would flow in branch A and B would be 5 amperes. Now, if 5 amperes has to flow in this circuit between A and B after the switch is closed, which is 5 amperes in this direction, that means this 5 ampere current can be distributed as shown over here. I is my 5 ampere current. This 5 ampere current, which is equal to I, can be distributed along the two branches through which this current is coming in from, and since the impedances are equal, it would imperatively mean that 2.5 ampere is coming in this direction on branch of impedance 10 ohms, and similarly 2.5 amperes is also flowing in to the other 10 ohms impedance, and that's how by KCL 2.5 would add up to 5 amperes, and that's how the current distribution on actual network can happen. Now when this current distribution actually happens, what do we see? What we see here is that, let us come back to this circuit actually. So here let me take this circuit again for a moment. So if IB was 7.5 amperes, that means the current which was flowing along this 10 ohms resistance when the switch S was closed, it was equal to inverse proportion. So 5 ohm impedance would come in here because of the inverse current distribution, which would give me 2.5 amperes, and similarly the remaining 5 amperes is coming in here. Why am I getting 5 here? Because 7.5 into 10 divided by 15, 2 and 3, 3 and 1.3 and 2.5, which gives me 5 amperes. So current always distributes in inverse ratio of the actual current distributions. So now if I compare these currents 7.5, 2.5 and 5 after the switch is closed, and for a moment observe what is happening over here. What I see here is that this IAB current is matching with the 5 ampere current which was flowing, and this circuit here is basically the pre-fault condition. Now if you look at the pre-fault condition, in the pre-fault condition the current here was IB naught, which was 5 ampere, and the current here was also 5 ampere, IAB did not exist. Now if I superimpose 5 ampere with the currents shown over here, the actual currents which would now flow would be 5 plus 2.5, which is 7.5, and the current, let's say if I have to find I10 here, I10 would be, the previous current is IB naught minus 2.5 because the current direction is reversed, which would give me 5 minus 2.5 to be 2.5 amperes. Now these numbers, they happen to match with the numbers which are shown over here. So that means by current distribution, I can easily find the new change in currents, because when the switch is now closed, so the new change in currents can be obtained through Thevenin's theorem, and then those Thevenin theorem results could be superimposed on the pre-fault or condition, or the condition where switch was still open, and correspondingly find my new current 7.5 amperes, 5 ampere in the switch, and 2.5 amperes through the 10 ohm circuit resistance. So essentially this notion is a very beautiful notion, and coincidentally the same can be applied for the complicated fault analysis for actual power networks. It can easily help in doing fault analysis by extensive use of the system admittance matrix or impedance matrix, basically Y bus or Z bus. And in case we have a network where the machines would usually be loaded, so the pre-fault current would be the usual steady state current which can be obtained from the power flow analysis. We would also have a similar evaluation done in stability analysis when we will deal with disturbances and their impact on stability. And after the fault, we basically apply the Thevenin's theorem, find the change in currents, and superimpose or apply on the pre-fault currents, which are the steady state currents, to find the overall post-fault current. Remember, Thevenin's theorem is applicable only for a circuit with sources of same frequency, because Thevenin's theorem would heavily depend on evaluation of Thevenin impedance, and Thevenin impedance would again be, in a phasor domain representation where phasors cannot be defined for circuits where there are two different sources. So that's the reason why Thevenin's theorem is not applicable for sources with different frequencies. So, coming to balanced fault analysis, the first case, as already explained, this occurs when all the three phases of a line or bus are equally affected or equally shorted. It is one of the most severe occurring fault, and why it is called severe, we'll understand that when we correspondingly go into the fault current evaluations. It is severe fault because the change in current in three-phase fault is the significant, the voltage drops are also significant, but it has the least frequency of operation because it is very difficult for such an event to occur. So basically these are most severe and least frequently occurring faults. All the three phases are equally affected, and hence this fault is called as a symmetric fault or a balanced fault. Generally, the magnitude of fault current, it would depend on the subtransient reactance of generator and the corresponding equivalent impedance of the overall network. The purpose of fault analysis, as already explained, is to find the worst case fault currents and voltages so that we can make a decisive information about the different protection elements that are used for protecting our electrical network from such electrical faults. So, in case the fault occurs with fault impedance 0, we would call it as a dead short circuit fault or a bolted fault. In case the fault occurs with non-zero fault impedance, then we would call it as a non-bolted fault or a non-zero metallic fault. Usually, again, occurrence of bolted short circuit faults is a rare event. Usual faults, they also appear through some non-zero fault impedance. By fault impedance, I mean that if the current which was actually supposed to flow from source to load, if it is getting diverted because of some short circuit, then this short circuit path also has its own impedance. Obviously, this impedance is lesser than the network impedance, otherwise the current would have flown through the network itself. So that's the essence behind having zero or non-zero fault impedance. Having zero fault impedances, it's a very rare event. Certain assumptions that would help us in simplifying or sort of bringing down the effort required in fault analysis. We'll start with the three-phase faults first. So our faulted network, we will analyze it through Thevenin's theorem, and while applying Thevenin's theorem, we would extensively make use of the Z-bus matrix, which would depend on what is the Y-bus matrix. The evaluation of Y-bus remains the same as we discussed earlier in the power flow analysis module. Certain assumptions that would help in evaluating or simplifying the fault analysis exercise is that all elements which pertain to reactive power devices like shunt capacitances, admittances or susceptances, their effect can be considered negligible, their presence can be ignored, because even if these elements were to be considered, what would happen is that while finding the corresponding Y-bus or Z-bus, the overall system impedance would increase in the presence of these elements, and as a result the corresponding admittance would decrease. While ignoring their presence, what we are considering is that the fault impedances would go down, the corresponding admittances would go up if these are neglected, and in a case where the fault impedance or the Thevenin impedance tends to go down, we would still be able to get the worst possible fault currents, which is a okay estimation or a worst case estimation, and that's the reason why we go for risk averse estimation. Similar analysis or understanding also goes for resistances. All resistances, line resistances can be neglected. Reason being the same. There is another logic behind why resistances can be ignored for safety purposes, that if you recollect the definition of time constant that we had in the two previous lectures, the time constant in a RL inductive circuit was equal to L by R. So in a circuit, if we are ignoring the presence of resistance as indicated here as one of the assumptions in three-phase fault analysis, the overall time constant would tend to infinity, which would mean that the corresponding fault analysis that we are doing with negligible fault resistances, the subtransient period or decaying DC component would never ever die off. That would mean that the current that we would estimate, which are the worst case or risk averse estimations, they would continue till eternity, and essentially we are not losing anything while ignoring the presence of resistances. That is point number one. Point number two, if resistances would have been considered, then the corresponding system impedance would have gone up, the current levels would have gone down. We are, by ignoring the resistances, trying to find a higher level of current, which could be the worst possible current, and this difference between the actual current with impedances considered and the current without considering of impedances, it provides a sufficient safety margin for different protective elements like circuit breakers and relay to work with. So these assumptions, they essentially help in providing additional margin. They also help in bringing down the complexity involved while not considering these elements. All synchronous machines, be it generators or motors, since it is a subtransient period, so they are represented by their internal EMF and the direct axis subtransient reactance. All static devices, that is non-rotating devices, their presence can be ignored, because as seen in the previous lecture example, even if these loads were to be considered, which could be non-rotating in structure, the steady state load current quantum is much smaller than the current that we would encounter during faults. So basically we are trying to get rid of the pre-fault condition in itself. That is point number one. Point number two, non-rotating loads, they don't have any magnetic flux, so essentially they won't have any experience of subtransient, transient or steady state variation in them at all, because there is no magnetic flux which is varying with time. Obviously, in case of transformers, the machine has a magnetic behavior, but there are no rotating devices involved at all. So transformers also experience these inrushes or surges, but there the behavior is completely different compared to synchronous machines. Rotating loads like synchronous and induction motors, they can contribute to fault current, and such devices, they have to be represented carefully through their internal EMF and the least quantum of direct axis subtransient reactances. Uh, Going ahead with this logic of ignoring non-rotating faults, pre-fault conditions can also chosen to be at 1 at an angle 0 pu for all bus voltages, because if we consider this condition, then essentially we are ignoring the flow of normal pre-fault current. If as an engineer we want to find, oh, we are very sacrosanct and we should not make this assumption of having flat voltage profile across all buses in the network, go ahead, fine, no issues. Perform actual nonlinear power flow analysis, find voltages and find the pre-fault currents. But the overall actual fault current that we would observe without doing power flow and with doing power flow, the difference in currents would not be significant, and that's the reason why this sort of assumption works well from the practical consideration perspective. In the next lecture, we will extend this Thevenin's theorem discussion for understanding how balanced faults can be analyzed and see a particular corresponding example if possible, and continue with the unbalanced faults in the upcoming discussions. Thank you.